Hey everyone, Max here. So this is going to be part 2 of the chi-squared videos, okay? And what we're going to start doing is we're going to walk through 2 examples of using the chi-squared. Our first example is going to be on a test for independence. Oh, I think I may have to turn the pen on. Let's make it so you can kind of read it. And so what a test for independence here is, does a relationship exist between at least variable with another. This is the main question. This is the main question the chi-squared test is asking. Okay. And so when we're trying to answer this question, essentially what we're going to be doing is we'll have our null and we'll have our alternative hypothesis. But really the main idea here is going to be computing the statistic and what's going on behind that. Because we'll talk about the null and alternative hypothesis, but by now you're most likely familiar with how to formulate those. So I'm going to be pulling from the lecture notes posted on my class website, and I'm going to just copy a table real quick. So I'm going to pause the video while I copy that. So we've got this table that I just finished drawing. And let's suppose we're wondering if a relationship exists between age and living situation. So just as a quick aside, our alternative would be there does there does not. Okay. And also, if you recall earlier, the fact that a chi-squared always looks like this, all of our tests are going to be one-sided. All chi-squared tests are one-sided. But if we wanted to make it two-sided, we could do that. But for our purposes, they'll only be one-sided. Okay. So essentially, now that you have some data table, you surveyed 8 people ages 19 to 22, you added the total up for that, you asked their living arrangement, okay, you get this table. So it's basically like, so we have a table. Now what? What you want to do is you want to start processing your data. So you can actually determine a theoretical expected count. The idea of an expected count is if we survey again, under the null hypothesis, and based on this data, how many would we expect in each cell? Recall that one little square here is a cell, okay? And so that is, if you're 19, where do we expect, like how many people do we expect out of 540 19-year-olds? How many do we expect to live in group quarters, like a dorm? Okay, what we surveyed was 58, but based on this and under the null hypothesis, how many would we expect in a theoretical count? So this expected count has a formula. And it is essentially the observed count. Oh, sorry, wrong formula. This is going to be your row total times your column total over the overall total. So if you look at what's going on here, this row total is, I fixed this total, say, for 19-year-olds, 1357. Okay, let's do a little highlighter. Okay, so when I look at this total, I'm essentially looking at the entire row here for people living at their parents' place when I look at the row total, okay? But now when I pick a column total, let's say for 20-year-olds, I'm now looking at this entire total for 20-year-olds. And where this highlighting intersects, oh, we can use like a rainbow glitter. Let's use rainbow glitter. Where this intersects is in that cell for 20-year-olds that live at their parents' place. And then when you divide by this overall count, this overall total, you end up essentially with the proportion of this and how it relates to the overall total. So when you multiply these two together, and then divide by this overall total, you'll end up with a theoretical count of, if you, under our null hypothesis, if you were to sample again and everything, this is how many people you would expect. So an example computation for, say, 20-year-olds that live in their parents' place, you would do, let's do the darker rainbow color, 1357 times 766, and you would divide by 2984, which is approximately some number I need to compute, which is approximately 348.35. Okay. Specifically, this is how many we would expect under our null hypothesis if we were to do this again for a theoretical count. And you have to do this for every cell. So you would say, fix this row, and you could fix this column. And that would be for own place in 21. And then, and you do this for every cell. So I have, of course, done it already. I realized I could use a ruler function on this, so I tried to make straight lines. And this is what those theoretical counts end up being, okay? We end up with that 348.35, the 364.26, And these are all theoretical counts. That is the highlighter still. Okay, and the reason we're computing these expected counts is because the chi-squared statistic takes the following form. So the chi-squared statistic of new degrees of freedom is our distribution, okay, for some random variable, but the chi-squared statistic denoted chi-squared. The reason I wanted to emphasize this is if you write the degrees of freedom, this will be a distribution, but if you just write this chi-squared, what you're denoting here is you're denoting a statistic. So denoting statistic is computed as follows. It's simply the summation sorry, everything's going crazy. I'm knuckle dragging quite literally. Okay. You have your observed count minus your expected count squared. And note that because this is squared, you could do expected count minus observed count over your expected count. Oh, and I wrote a summation equals, but you all, being astute students, knew that that was erroneous, and it's actually just this sigma I, where I indexes over the cells. Okay. So an example to compute this thing, I'll set it up, but first we're going to need all the observed counts, which will be so 324, and then we would need the expected count, which would be 245.57 squared. And the expected count, of course, is going to be 245.57 plus, so here I'll write a chi-squared equals. And this is going to be a 348.35. This is a 348.35. This is going to be a 337 plus. This is going to be a 318. This is going to be a 318, right? We've got a 318. 324, 378. Oh, see, I missed a column, but it's a summation, so don't worry about it. We'll be okay. We just have to make sure I matched everything up appropriately, which I don't think I did. Okay, so let's just put all these expected counts in. Okay, I'll get this out of the way. And since I can see them both now, we can just do 345. This can be 378. Oh, I had erased. $378 minus And this will be 348.35 squared over 348.35 plus 337 minus 364.26 squared over 364.26. And notice that what I'm going through here is I'm not going over the expected count for these totals. We're only doing the expected counts. That was not at all what I wanted to do. We're only going through the expected counts for the actual data, right? So we don't want to go through on these columns, because if I were to do this total, right, the total expected count, if we were to do this, okay, would just be, let's say we computed it for living arrangements total on parents' place. That would be 1357. The column total would then be 2984 over 2984, which just simplifies down to your row total. So we don't actually go over the totals for this. We just go over the actual data points that we would care about. So we would continue this process all the way through all the other ones. And so we'd get down to other, we'd have 9 minus 8.77, oh, sorry. 5.58 over 5.58. And this is squared. And this is approximately another value that I need to compute. So 1 second. 193.5. And this is actually very big. And when you go and you look at all the statistic values and the p-values and everything, you'd find that this essentially means that we would end up rejecting our null hypothesis, and it would be significant at almost every level. But the one thing we need still is our, and I'll zoom in, is we still need our degrees of freedom. Okay, because our degrees of freedom is what's going to tell us whether or not the statistic value is actually big. So this statistic value of 193.5 is definitely large. If nu is, say, equal to say 1,000, but is definitely not that large if nu is equal to, say, 1. So you need your degrees of freedom, otherwise you're not going to be able to do this correctly. So how do we compute these? And this is actually what can be kind of tricky. In this case, I'm going to write the degrees of freedom, and then I'm going to explain why I got that. And this is r minus 1, so number of rows, times the number of columns. This is number of columns. And they're both subtracting 1. And the reason we did that is because in order to get all these expected counts and everything, we actually needed both the rows and the columns to do this, right? If I were to remove just this, I could look at this total here and that total there, and I could figure out what that value was. But if I took this total away and just erase that, you'd be able to figure out what this is, but you wouldn't necessarily know what that total is for sure. So it's all contingent on what information you need. And we'll find that you can actually go all the way down to say like an r minus 2 times a c minus 3. And we won't be dealing with those cases in this class, but those are possibilities. Another one that we'll actually be dealing with is say just r minus 1, or just r times c minus 1. Okay, so these can change, and you just need to think about essentially the context of your situation. Okay, so this implies just up here, just going back to this r minus 1, c minus 1. So we had 4 columns, right? 19 through 22, right? So we're going to have a 3 there. But then we had 5 options, right? So if we look, 1, 2, 3, 4, 5, 1, 2, 3, 4, right? So our degrees of freedom is equal to 12, which is equal to nu. Okay. Now there's one other type of problem I want to discuss that chi-squared can come in handy with, is test best fit distribution. Test for fit of distribution. And essentially what this is if we were to do, say, the example in your book is if we have births, there's this hypothesis that essentially fewer babies are born on weekends. So we have the day, we have the number of births, okay, and we have some data, and I'll fill that in real quick. And so that's the data, is essentially we have days, births, and what we're trying to see is, well, our alternative hypothesis is babies take the weekends off. Our null hypothesis is they work 24/7. So that is just more babies are born on the weekdays than the weekends, and we're just going to test that to see if, well, actually you are going to see fewer babies on the weekends. And from our data, it kind of looks like it. But what the chi-squared test is going to do here is it's going to give us statistical backing to our claim, or it's going to essentially show that we don't have very good statistical backing. And so in this case, we would compute the expected count, right? But in this case, because we're not dealing with different column totals, we just have this row total, it's actually going to be fairly simple, right? Our entire total is going to be 140, right? If we just add all these up, we get 140. But the total number of days, the probability of being distributed over these things is 140. Sorry, it is this probability. This is not the expected count. Well, it is actually going to be the expected count. It's 140 over 7, which is just 20. Because if they work 24/7, right, you'd expect to see 20 in each of these columns, okay? And where this is coming from is essentially we found the expected count here, but under the null hypothesis that they work 24/7 and that there is no essentially relationship with this idea of weekends and weekdays for births, we just divided the row total by the column total. And this is just because it worked out in a nice way mathematically for this to be 20. Okay. So what we needed here, it was the expected counts. That makes them all 20, right? And that's quite nice, so I'm not going to fill in another table. So we want to compute the chi-squared statistics. So we want to compute chi-squared. So this is, again, it's observed minus expected over expected, right? So you have 13 minus 20 over 20. And essentially, because they're all going to be over the same expected count, I'm just not going to write that. I'm just going to write it like this. 1 over 20. Okay, I'm going to do 13 minus 20 squared plus 23 minus 20 squared plus 24 minus 20 squared plus 20 minus 20 squared plus 27 minus 20 squared plus 18 minus 20 squared plus 15 minus 20 squared. And note that these values are always coming out positive. If you ever get a negative chi-squared statistic value, you did something incorrectly. Okay, and let's just make sure 1, 2, 3, 4, 5, 6, 7. Okay. And then this shakes out to be about, 1 second. This shakes down to be about 7.6. Okay. And now the big question is, what are the degrees of freedom? So in a naive approach, most people would want to do this r minus 1 times this c minus 1. But if you look, row minus 1 is 1 minus 1. Columns here is 7 minus 1. This gives us 0. And earlier in the other video, I said that a chi-squared can never have degrees of freedom 0. Okay. So that clearly isn't correct. But we also didn't really need the rows, right? If I removed a row, you wouldn't be able to get any information. So we actually need the entire row, okay? However, if you look at the column, I don't need the entire column to figure out what's there. I can actually remove one of these columns, right? Because I know that this is 140, I could remove, say, Friday, and you'd still be able to figure out that that was 18. However, if I removed the entire row, you wouldn't be able to figure anything out. So essentially, we only need c minus 1 of these things. So you need the entire row. Oh, let's make this black. You need the entire row, but you only need one of the columns. So this implies 1 times 7 minus 1 is equal to 6. And you'll find that our chi-squared statistic means that because of our degrees of freedom with our chi-squared statistic, we should fail to reject the null hypothesis in this case. Let me check that. We can check on the notes. Yeah. Okay. So that is how you do various contingency table tests.